together. Today I want to talk about the working principle of a reflectometer. And here I sketched in the principal setup of a reflectometer. The reflectometer consists of a signal source, and we have an isolator to protect our signal source against back reflections. And here I assume to have an ideal directional coupler. Ideal directional coupler means that we will have no coupling, for example, between the port 1 and port 4, and only a coupling between port 1 and port 3 and port 2 and port 4. Further, I assume that I can measure the wave amplitudes before, which consists of an absolute value and phase, and I assume I'm able to measure the complex value of B4 and B3. And here we have our load reflection coefficient, which we call device under test. And now we can talk about the working principle of this reflectometer. And we see our generator will generate a wave amplitude A0. And here I sketched the signal flow graph of this reflectometer, and I only included the signal passes which are relevant to the working principle of our reflectometer. So in the first step you see that the A0 will enter into our directional coupler, and then a portion of this will be coupled to the port B3, so we can here measure the wave amplitude B3, and the wave amplitude B3 will be given as C times A0. On the other hand, we have A0 and A1 here, and a part of the essential part of the wave A1 is transferred to B2, to our device under test. And here we have the transmission coefficient, which is very close to 1, but which introduces a certain phase. And now our reflection coefficient RL will create the wave amplitude A2, and the wave amplitude A2 will be coupled to B4. So we can get for B4, the wave amplitude B4, we will get, this is C times RL times the transmission coefficient T times A0. So we assume that we know both wave amplitudes with absolute value and phase, and so we can calculate the ratio of these two complex wave amplitudes, and this we will call the measured reflection coefficient. And if you see this equation, then you see that the C will cancel here and the A0 will cancel, and we will see that the measured reflection coefficient is essentially equal to the reflection coefficient of the load. But here we have a problem. Of course, this value is close to 1, but it will introduce a certain phase. So we will have here a systematic error, and as soon as you have a systematic error, then you can do a calibration to get rid of this error, and this I will explain in the next step. So I sketched here the principal setup of the reflectometer, and we saw that even if I assume to have an ideal directional coupler, this will lead to a systematic error. And the equation which represents this systematic error is given by this equation here. We have Rn, the measured reflection coefficient, is equal to T times RL. So the transmission factor of a directional coupler is normally very close to 1, but it will introduce, of course, a phase. And if I want to measure the reflection coefficient with absolute value and phase, then we have to correct for this parameter. And as soon as I have only one error parameter, I can use one calibration standard. For example, we can use a calibration standard called short. We know if I have a short RS, then the reflection coefficient will be equal to minus 1 of a short. So we in the first step we must connect, instead of our load reflection coefficient, our standard, our calibration standard. And if we carry out then this measurement, then we measure the calibration, this calibration standard of a load, which will be equal to minus t times, which will be equal to minus t. And the second step, we again measure our device under test, and which will result in the reflection coefficient Rm now. And in the third step, we now can do the correction, which means we resolve this equation for Rl, which results in this term, and of course then we insert our measured reflection coefficient of our standard into this equation and do the correction. So this will give us the correct result of our load reflection coefficient with absolute value and phase. But you see, this is only possible with modern computers, because you must do some complex calculation here. And for example, for each frequency step, you measure this calibration standard and you have to carry out this correction. I want to discuss now a further problem of a directional coupler. Up to now we assumed an ideal directional coupler, but now I want to assume a coupler, a directional coupler with a so-called find isolation. What does this mean? Up to now we assumed that there was no coupling between the port 1 and the port 4. But in a real directional coupler we will also have a coupling between port 1 and port 4. So even if this coupling is very small, it will exist, and I call it now epsilon here. So epsilon will describe now the find isolation, which means, so again, B3, the equation for B3 will not change, so B3 will be still C times A naught. But you see now what B4 will consist of two elements. One element we already know, but now we also have a further element and this element is now plus epsilon times A naught. So a very small part of the wave amplitude will be coupled to port 4 if we do not have an ideal directional coupler. And of course this will then change also the equation here. And of course here we will get, if I cancel now A naught C, then I will get this term, which we already know. This is the transmission factor will change our measured reflection coefficient, but we will also get a further term which will be equal to epsilon over C. And now you can think of under which circumstances this term is has the biggest influence. Then you will see, as soon as I want to measure very small reflection coefficient, then this coupling, this unwanted coupling, will lead to a certain measured reflection coefficient, even so this reflection coefficient does not exist. And so we will define now as a figure of merit of a directional coupler I will call the so-called, define the so-called directivity of a directional coupler. And this directivity of a directional coupler is given in dB. It's minus 20 log epsilon over C, the absolute value, and then we have the so-called directivity of this directional coupler in dB. And if I, for example, use now the normal notation using the S parameter, then the directivity would be given by minus 20 log absolute value of S41 divided by absolute value of S31. And this directivity is now a certain figure of merit, and it should be as great as possible.